Welcome back to Power Electronics, and this is part 2 of a 2-part set of videos. We are in our sequence for the DC to AC inverters, and in this second part of the video, we are going to continue on with the 6-step 3-phase inverter, and let's look at the overview. And for this video, we're going to go back and review part 1 of the video, and that was the 6-step 180-degree modified sine wave inverter waveform. And then using that waveform for this video, we're going to compute the RMS value of the line to neutral phase voltage, and we're going to focus on the A to neutral. But the RMS value for the B to neutral and C to neutral for this 3-phase waveforms are the same. We're going to find the Fourier series coefficients for the waveform, and then we're going to use that, and there's a couple important things that'll come out of that. First, that our third harmonic is equal to 0 for this waveform, which is somewhat important when we look at power quality of the waveform generated. And then finally, we're going to show that the total harmonic distortion for the line to neutral phase voltage waveform that we generate with the 6-step 180-degree conduction modified sine wave inverter is 31.1%. That's for the line to neutral phase voltages. You can be shown also, if we looked at the phase to phase voltage, that total harmonic distortion is also 31%. But we'll save that for another time. Again, let's review. Here we show a 3-phase Y connected load. We have our 3 voltage sources, all 120 degrees apart in phase angle, and our load is connected in a Y. And recall that our line to neutral is measured between a neutral conductor and one of the phase lines. So this one right here is A to neutral. Likewise, we could look at B to neutral and C to neutral as well. So that's our 3-phase load. And also go back in part 1 of these videos, we showed how to create this waveform down here, and that's our modified sine wave from a 6-step, and we see the 6 different steps here, S1, S2, S3, and those correspond to the logic levels associated with our switching on our 3-phase half bridge over here on the right-hand side, connected to our Y-connected load. And switching these with 180 degrees of conduction cycle, and again I show 720 degrees or 2 cycles of switching waveforms here, results in this modified sine wave that has pulse values of 1/3 times our DC voltage, 2/3 times our DC voltage in the middle, and then goes down to -1/3 and 2/3. And again, that is the line to neutral voltage for our A phase. Our B phase and C phase would be 120 degrees delayed, and here we show, here's our VA to neutral, VB to neutral, and VC to neutral waveforms. Again, you can see the phase shift associated with these waveforms. Now let's compute the RMS value of this sine wave, or this modified sine wave, and I'm going to focus on our A to neutral waveform. And recall, with root mean square, one of the first steps we do is we want to square our waveform. And so this lower graph is the square of our waveform. As you can see, when we square 1/3, we're going to get 1/9. And it's 1/3 times our DC value that's supplied to the bridge. So we'll get 1/9 times VDC squared. And then when we square 2/3, we're going to get 4/9. And when it is going through the inverting or negative cycle, when we square that, we're also going to get a positive wave. So the first part is squaring. The second part is taking the mean or the average. And because our waveform is symmetrical, I really only need to take the average over 180 degrees. So I'm going to take the average of just half of this waveform. And so when I take that average, it's the area divided by the total duration. And so that area is 1/9 VDC squared times 60 degrees plus 4/9 VDC squared times 60 degrees, plus, again, another 1/9 times VDC squared times 60 degrees. And we divide that all through by the total time, which is 180 degrees. And it's a little bit interesting because I am, as I said before in previous videos, I'm representing time in a normalized scale. And here we're in degrees. And so this axis is actually 360 degrees times our fundamental frequency of our waveform times t. So if our fundamental frequency is 60 hertz, that would be a 60 in there. If we are representing our waveform in radians, not in degrees, then this axis would be omega naught t. So again, just different scaling depending on how you want to represent the axes. Now we can solve this equation. Again, this is the mean of the square of our waveform, and we see the 60 degrees would factor out divided by the 180 degrees, and that would give us a 1/3 in the front of this equation. The VDC factors out as well, and then we're left with 1/9 plus 4/9 plus 1/9, and that's equal to 6/9 or 2/3. This whole equation is equal to 2/9 times VDC squared. And then the final step in the root mean square process is to take the square root. So if we take the square root of this value right here, our RMS value for the phase to line voltage of the 6-step 180 degrees is equal to the square root of 2 divided by 3 times VDC. So that's an important one. We'll probably want to put that down in our notes and keep that somewhere. So that's the RMS voltage. And we're going to use that later because that's going to allow us to calculate the total power in this waveform when we compute the total harmonic distortion. So before we compute the total harmonic distortion, one of the things we'd like to find out is what is the power in the fundamental harmonic, our B sub 1. For this waveform, it has odd symmetry, so our A sub 1 is going to equal 0. So we'd like to find our Fourier series coefficient for B1. And one of the ways we can do that is through superposition. So we're going to use superposition on this problem. And we see that our waveform is the summation of a square wave that has no angle offset with a height of 1/3 and minus 1/3, so that's right here. And if we add to this other waveform that has a theta equal to 60 degrees, we will get the resulting waveform. So I have two waveforms that when we superimpose them together give us our modified 6-step waveform. And let's look at the Fourier series coefficients. And the Fourier series is a linear operation, so I can just use superposition. Recall from the past video, this has Bn equal to 4 times the amplitude, and the amplitude is VDC divided by 3 all over pi n. So that's the Fourier series, and this is for n equal to 1, 3, 5, 7, all the odd harmonics. The even harmonics are equal to 0 for this waveform. And then also recall, I'm going to do the Fourier series for this second one. It is also equal to 4 times VDC over 3 pi n, but we have the factor of cosine n times the offset angle, and for here we're starting this at 60 degrees. And again, I'm doing this in degrees. You could also do it in radians, and 60 degrees would be pi over 3 radians if you're doing it in radians. So the next step now is to combine these two. And when we combine these two, we get 4 times VDC over 3 pi over n times 1 plus cosine n times 60 degrees. Now let's take a look at this term right here, n at 60 degrees. And again, n is going to range from n equal to 1, 3, 5, 7. And so we are going to be cycling this n starting at 60 degrees. And I'm going to just put an imaginary axis here and show us at 60 degrees. So cosine of 60 degrees is 1/2. And there's 60 degrees right there. And then we're going to go over 120 degrees, right? So n equals 3. 3 times 60 is 180. And our cosine angle is -1. So at -1, we have a 1 plus -1. This term is going to be 0 when n is equal to 3. And then when n is equal to 5, we're going to come down here, and our value will be 1/2 again. So 1 plus 1/2 will be 1/2. So here's n equal to 3. This is n equal to 1. This is n equal to 5. Here's going to be n equal to 7. So it'll be 1/2. N equal to 9 will be -1. 1 minus 1 is going to be 0, so on and so forth. So we see that this term, 1 plus cosine n 60, is equal to 1/2 for n equal to 1, 5, 7, 11, not 15. Let's see, 1, 5, 7, 11, 13. So everything that is not a factor of 3, 9, 15, and such is equal to 1, 5, or that's equal to 3/2. Putting that back into the equation, we find now that our B sub n for the modified sine wave is equal to 4 VDC divided by 3, I'll write it this way, n, times 3/2, because this term will either be 1/2 or 0, and the 3's cancel out, the 2's divide through by 2, and so we see that Bn is equal to 2 VDC divided by pi n, or n equal to 1, 5, 7, 11, 13, 17, so on and so forth. Our third harmonic is equal to 0 for our 6-step modified sine wave. And you probably want to write this equation down in your notes as well. Finally, we can compute the total harmonic distortion of the 6-step modified sine wave and recall that our total harmonic distortion is equal to, and I'm going to write it in this form, the power total minus the power in the fundamental, because that's going to give us the power in all the other harmonics, your second, third, fourth, so on and so forth, all divided by the power in the fundamental harmonic. And we multiply this by 100% to express the total harmonic distortion in percentage. For these calculations, I'm going to assume a resistive load, and I'm going to assume a resistive load equal to 1 ohm. And it will normalize, because if I do the power calculations, there'll be that term in the numerator and denominator. And so really we'll be looking at just the voltages. So to look at the power total reference to a 1 ohm load, I really just need to look at the voltage squared. And the power total reference to a 1 ohm load is equal to our RMS value squared, which we just derived earlier. And the power in the fundamental is equal to B1 squared divided by 2. And we've just derived that as well. So that was 2 VDC over pi, and if I square that term and divide by 2, that's going to give us the power in the fundamental. And let me calculate the power in the fundamental component first. That's equal to 4 VDC squared over pi squared divided by 2. These cancel out, and so that's equal to 2 VDC squared over pi squared. The total power is equal to our RMS value squared, which is equal to VDC times the square root of 2 over 3. Let's square that whole term. So that's VDC squared 2 over 9. Now we can plug these two values into our total harmonic distortion equation, and I'm going to do that on a fresh sheet. And so we get our total harmonic distortion is equal to the square root of our total power square, which is going to be 2/9 VDC squared divided by the power in the fundamental, which is equal to 2 VDC squared divided by pi squared minus 1. And I'm using the form of, recall, if I look at power total minus power 1 all over power 1, that's just the square root of PT over P1 minus 1. There's a couple different forms of this, and we have to multiply this by 100%. And we see the VDCs are going to cancel out. We've got a VDC canceling out there. The 2's cancel out. And then this pi squared comes up to the numerator. So this is equal to the square root of pi squared over 9 minus 1 times 100%. And if you plug that number into your calculator, you should get a number of 31.1%. And so our total harmonic distortion for the modified sine wave is 31.1%, which is pretty good. All right, so that was the analysis of the RMS and the total harmonic distortion in our 6-step 180-degree conduction wave with our line to neutral waveform. And one of the key points is there was no third harmonic. Our third harmonic was equal to 0 in that waveform. So that's a pretty nice property. The other harmonics were given by this equation. Bn equals 2 times our DC voltage divided by pi over n. And we only had harmonics for the 1st, 5th, 7th, 11th, 13th, so on and so forth. And finally, we showed that the total harmonic distortion was equal to 31.1%. So that wraps up the video sequence for the 6-step 180-degree conduction waveform. Again, I've mentioned in the first video of part 1 of this sequence that you can do this analysis also. There's a 120-degree conduction type of waveform, and there's a 150-degree type of conduction waveform. And we can also look at the line-to-line phases, which I have not done here. The analysis and the methodologies follow this way, this approach that I showed in these 2 videos if you want to continue on further. So that's it. So thanks for watching.